Hi, the lecture note series of Calculus 2 will be completed with this final session. In this part of the notes, we talk about multiple integration, including double integrals, and also double integrals is discussed in different plane regions or space regions, where the first one is the double integrals over plane regions. Then we will discuss polar coordinates, and then we will join these two topics and mention about the double integrals in polar coordinates. Then we will go through triple integrals as the multiple integral, where for the triple integrals, first we will define the triple integrals in Cartesian coordinates, and then triple integrals in cylindrical and spherical coordinates. Now, after this simple or brief summary about the topics that we will cover in this session, now we will turn back to the double integrals, and we will talk about the double integrals in plane regions. So we will say that the double integral of a function f over a rectangular region R, in this case note that the region is a very special region which is a rectangle, then this integral is denoted by two integral notations over the rectangle R, f of xy dA, where in this case we are saying that f is integrable over the region that is the rectangle R. But the double integral over a rectangular region can be extended to double integrals over plane regions, which are called domain in this case. And in this case, we just write it as a double integral over d f of xy dA, and also we say that f is integrable over the double integral. To enable us for the evaluation of a double integral, we will give a theorem named as the Fubini's theorem, where for the Fubini's theorem we have two steps. That is, this theorem gives us a way to evaluate or enables us to evaluate a double integral depending on two types of regions. The first one is a y-simple region. That is, in the y-simple region, y changes in between functions. Certain those can be constants also, but it can be functions, but x changes just in between two constants. That is, it's a region, and in such a case the double integral of f over the domain D, which is a y-simple region, can be written as the iterated integrals a to b and then g1 of x to g2 of x. That is, the inner integral is evaluated with respect to the variable y, where the boundaries of the integrals changes from g1 of x to g2 of x, and the outer integral is evaluated with respect to the variable x, and x changes from a to b. The second type is an x-simple region. In this case, by saying x-simple, we understand that x may change in between two functions depending on y, such as h1 of y and h2 of y, and y changes between the constants. In such a case, a double integral can be written again as an iterated integral, c to d and h1 of y to h2 of y. That is, the inner integral is evaluated with respect to x, where the lower boundary of the integral is h1 of y and the upper boundary is h2 of y, but y changes from the constant c to d. Note that the integrals in both equations we mention here, this one and that one, are called iterated integrals, and if the regions are either y-simple or x-simple, then we can evaluate the double integral using these two types of iterated integrals. But also, if a region can be divided as the finite union of x-simple and y-simple regions, again the integral can be evaluated, that's the double integral, can be evaluated using these two types of regions. As an example, we are saying that in this case the function f of xy is xy plus x square, and we want to evaluate this integral over the domain D, where domain D is a region where y is smaller than or equal to x is smaller than or equal to 1, and x is larger than or equal to 0. That is, if we draw this region, we can see what does it look like. But before that, let's make a simple discussion through that region. It says that in D, x may vary from 0 to 1, and D is a triangular region where, let me draw the region here. Note that in this case, y is changing from y equals 0 to the line y equal to x, and x takes the smallest value 0 and the largest value 1. So we can say that in this case, this region can be considered as a y simple region, but also it can be considered as an x simple region. And then if you want to write the double integral over this region, we see that y, that's the inner integral, changes from 0 to x, and outer integral takes smallest and largest value of x in the domain D, that's the triangular region, where the smallest value of x is 0 and the largest value of x is 1. So we just write them as the boundaries for the outer integral. Then we evaluate those integrals. First, the evaluation is made through the inner integral, and then we get this one. So when we put those values, then we evaluate the integral or outer integral, and then in this case we obtain the result that the integral equals to 3 over 8. Double integral can be used for different types of applications. One of the basic application of a double integral is the area problems. That's why we want to take a second example as an area problem, where it says that find the area of a region bounded by the parabola y equal to x square and the line y equal to x plus 2. In this case, we can sketch the region here, where this region says that this region can be again considered as a y simple region, because if you note that y changes from the line x plus 2 to the curve y equal to x square, where the smallest value of x in this case is -1 and the largest value of x is 2, which is obtained by those evaluations. So if you want to write the area of this region as a double integral, we can say that it is the double integral dA, because f in this case is taken as 1, which is one of the important property for the double integration. Then y changes from x squared, that's the parabola, to the line. This is the smaller value of y, this is the larger value of y, and the smallest value of x in the region is -1, and the largest value of x in the region is x plus 2. So we evaluate the integral and we get that this area is 9 over 2 square units or unit square. By this way, we can evaluate the area using a double integral over the plane region D. Now we will go through a new coordinate system, which is called the polar coordinates. Polar coordinates is not exactly the same as the Cartesian coordinate system. In the polar coordinate system, we have a pole, where it's mentioned here, and a polar axis. So this is the polar axis and this is the pole. So we have a half line or half real axis from 0 through the right hand side, and then we measure an angle using this polar axis in the counterclockwise direction, which is the angle theta, and on the ray of the angle we measure a length r. This length from the pole, that's origin, to this point is represented by r, and theta measures the angle that is measured in the counterclockwise direction using the polar axis, and any point on the ray of this angle is represented by r and theta. So in polar coordinates we have two variables, r and theta. R is the distance of this point on the ray of the angle from the pole, that's the origin, and theta is measured in the counterclockwise direction. It can be measured certainly as clockwise direction, but it is named as minus theta, or this minus sign shows us the opposite direction. If you consider the Cartesian coordinate system and also the polar coordinate system, assuming that their origin are coinciding, in this case we can find a relation using this right triangle between Cartesian coordinate system and the rectangular coordinate system, where the transformations between those coordinate systems can be given by these two equations. Note that here x is the distance of this point from the origin, and we can say that if you consider the cosine theta, it is x over r, or we can say that x equal to r times cosine theta and y equals to r times sine theta. In the opposite direction, we can say that r square equals to x square plus y square by the Pythagorean theorem for the right triangle, and tangent theta equals to y over x. Now, through the polar coordinate, we may give some examples. For in this case, a circle with center on the x-axis, say at the point A0 with radius absolute value of a, which is a circle tangent to the y-axis, and this circle in Cartesian coordinate system has the equation x minus a square plus y square equal to a square. If you want to convert it to polar coordinates or transform it into polar coordinates, in this case for x we should write r cosine theta, and for y we should write r sine theta. So it gives us in this case the equation x minus a square such thing. Then for x square we cancel a square, so we get x square plus y square minus 2ax equals to 0. If we make those substitutions, then we get that r equals to 2a cosine theta, that is the circle whose center on the x-axis, that is at the point A0, with radius a positive or absolute value of a, has the equation 2a cosine theta, where in a similar way we can find the equation of a circle which is symmetric with respect to y-axis, that is whose center is at the point 0a and the radius is absolute value of a, can be evaluated, which is r equal to 2a sine theta. But in this case, to make this discussion on the diagram, we can say that if we have r equal to a times cosine theta, it means that the radii of the circle is a, but the radius of the circle is a over 2 and the center is at a over 2 if a is positive. If a is negative, we have the opposite direction, that the circle is on the left hand side of the y-axis. Similar to this one, we can write r equal to a sine theta where a is positive. It is a circle symmetric with respect to y-axis whose center is at the point 0 a over 2 and the radius radii is a, that's the radius is a over 2 in other words. In this system we can sketch some curves more easily. One of the example is the graph of the curve r equal to 1 plus cosine theta. To make or to sketch this curve, we first give values to theta, which are the well-known angles that we learned earlier, and we evaluate the corresponding values of r. So we measure those angles. So for example, this is the radian 0, this is the radian pi over 6, this is the radian pi over 4, pi over 3, and so on. And we measure those, then we sketch a curve where this curve is called a cardioid. The polar coordinates can also be used in the double integrals, where in this case we can say that the double integral, which is given in rectangular coordinates, can be converted in the polar coordinates by using this equation. That's first we write the region in plane region is converted into polar region, and then for the function we have to write the function f in terms of the polar variables r and theta. So for x we write r cosine theta in the function, for y we write r sine theta. For dA in rectangular coordinates or Cartesian coordinates, we just write r d theta. But in this case we have to be careful, because dA in Cartesian coordinate system has two differentials, dx and dy, with different orders, either dx times dy or dy times dx. But in polar coordinates, for dA we have those three terms. That is, we have one more term which is r. dr and d theta are the differences, but we have r also here, which is also in dA. That's why for the conversions we have to be careful in this case. Let's have an example. In this example we can say that by mistake I turned back to the older pages, but let me turn back to the example now. Example says that evaluate the double integral over the region R, where R is given by these two inequalities or the order of inequalities, and this region is called consists of two circles, one after another, where in this case note that here we first convert cosine x square plus y square, because x square plus y square makes r square, and we can also write the other values. Then this region is called an annulus, means that it is something like that we eat in the morning times. This is the region that we cover in between two circles, and we want to evaluate this integral over that region. So we can write the double integral in the form that 0 to pi for theta and r is changing from 2 to 3, where it is the following thing. The ray, if you take an ray from the center to the boundary of the integral or the region, this ray changes from r equal to 2, which is the inner circle, to the circle boundary r equal to 3, which is the outer circle. And also the angle theta changes from the origin, that's from the x-axis, r equal to 0 theta equal to 0 radian, to pi radian. That's why we write this integral in this case in the form that r from 2 to 3 and theta from 0 to pi. But note that for dA we write r dr d theta, and for cosine x square plus y square we write cosine r square. If we evaluate the inner integral in this case, we have this result, and the conclusion follows, which is pi over 2 times sine 9 minus sine 4. After the double integral, we will discuss the triple integrals, where triple integral is again defined here, where it is represented by this notation. But we want to take your attention on one of the points. It's the following. We have a solid region, where the solid region is defined over a plane region R. So we can consider the triple integral in this case as the integral of a double integral with respect to z. where if we know the double integral over a plane region R, then we can evaluate this double integral once more with respect to the variable z, where in this case we define the triple integral. As an example, let's find the volume of the region which is given in the example. That is the region under this plane in the first octant. This is the plane, the green part is the plane, and this red or purple part is the plane given by the equation 3x plus 2y plus z equal to 6. Then we want to find the volume in this region in the first octant. So what we do in this case, we just write the triple integral. Note that z changes from z equals 0, that is the xy plane, to upper part is the plane z equal to 6 minus 3x minus 2y. So we are saying that in this case z changes from this region. Then we can measure the boundaries for x and y. So we are saying that z changes from 0 to this one, and then we can write dA in this case, or we can say that z changes from 0 to that, then we have the double integral here, and then we write the double integral. The evaluation is stepwise. That's first we evaluate the innermost integral and then the others. As a result, we get the value here that this is simply 15/4 square units. So we found the volume under the plane z equal to 6 minus, I didn't remember, 6 minus 3x minus 2y over the region. So this region, this solid region is obtained as 15/4 cubic units. In three-dimensional space, we also use two more coordinate systems, which are called cylindrical and spherical coordinate systems. In those systems, we can say that we use some types of variables, new variables, where those variables are defined in the cylindrical and spherical coordinates, such as the diagram that's put here. In cylindrical coordinates, if you take a ray from the origin to the three-dimensional space, any point on this ray is represented by r, theta and z. Z is the same as the Cartesian coordinate system, and r theta is exactly the same as we used in polar coordinates. That is, first we measure z and we take the projection on the plane. On the plane, this projected point is represented by r theta, so it is the point that is used earlier for polar coordinates. For the transformations, in this case, that is the conversions, we use the equations z equal to z, x equal r cosine theta, and y equal r sine theta. If you note that these two are the same as the conversion formulas or the transformation formulas for polar coordinates, or the transformation between Cartesian coordinate systems and polar coordinate system. Z doesn't change, it's exactly the same, but it should be written in terms of r and theta. In this case, the important thing is the area element dA and dV, where dV is represented as dA times dz. But if you remember that dA in polar coordinates for the conversion of a double integral from Cartesian coordinate system to polar coordinate system, dA equals to r times dr d theta. So we use the same idea for this translation or conversion. For the spherical coordinate systems, we use three different types of variables, rho, phi and theta, where if you again consider the same type of diagram, if you take any point in the space under this ray that's measured here, what do we mean by saying rho, phi and theta? Rho means it is the distance of the point from the origin. Phi is measured vertically, that is, it is the angle measured from the positive z-axis through this ray or the surface what it is. And theta is measured in a very similar way that is used in polar coordinates. That's we take the projection of this point on the xy plane, which is again maybe represented by some names, but we didn't write it, where theta in this case is measured starting with positive x-axis through this line projection of the ray measured here. So it is the line projection of the red line on the xy plane. So theta is the angle starting with positive x-axis through this line. And by this way we measure three variables in a spherical coordinate system. For the conversion formulas, we in this case say that x equals to rho times sine phi cosine theta, y is rho times sine phi sine theta, and z is rho times cosine phi. For more ideas, or if you want to learn more about this new coordinate systems, it is better to consult or read the lecture notes that is put in Moodle page, because we are just giving him here some summaries about what is mentioned for those topics. Where the distance formula in this case we can write as rho square equals to x square plus y square, where the volume element dv is somehow different. It is rho square sine phi d rho d phi d theta. Now let's have an example to apply to these two new coordinate systems. In this case the question says that express the volume of the solid S bounded by the sphere and the paraboloid z equal to x square plus y square. And now we want to evaluate this volume in spherical coordinates and in cylindrical coordinates. So if you want to make those evaluations in these two new coordinate systems, first it is better to make the transformations, or that's the conversions of those equations, two equations, in this system. That is, if you want to solve the problem in spherical coordinates, for x, y and z we have to write the conversion formulas that is given here for spherical coordinates. And for this equation, that is the equation of a paraboloid, again we have to use the same formulas. So we have to write the equations of those surfaces in spherical coordinates. If we want to solve the problem in cylindrical coordinates, again it will be the same. That is, we will make those conversion formulas. So in the first one, note that rho is changing in between 0 and square root of 2, phi is changing between 0 and pi over 4, and theta is changing in between 0 and 2 pi. There are two regions, because where those regions, if you look at the same example in the lecture note, it will be more clear for you, because here this is the PDF form, so the colors may not be so clear enough. But if we sketch that, there are two regions here which are measured through these two discussions, and then we can write the volume as the sum of these two regions. So we evaluate the integral of the inner part and the outer regions, which is given by this integral in spherical coordinate system. And if you want to express this integral or the volume in cylindrical coordinate system, again we have to make the conversion formulas. In this case, sphere equation has the equation r equal to z equal to square root of 2 minus r square, and paraboloid is z equal to r square. R is changing from 0 to 1 and theta is changing from 0 to 2 pi. Then if we want to find what this volume is, we can evaluate those integrals starting with the innermost through the outer integral, and we get the result. But our aim here is not to evaluate it, just express this volume in two coordinate systems. By this example, we complete the lecture notes of Calculus 2. So, we hope you enjoy your classes.